Hi. Now we are going to see formulae and problems in the chapter magnetic effects of current. First part, formulae and problems, magnetic effects of current, first part. To start with Biot-Savart law, magnetic field whenever a current is passing through a wire. The surrounding, there exists a magnetic field whenever current is passing through the wire. That magnetic field is given by dB is equal to mu naught by 4 pi ideal sin theta by r square in vector form mu naught by 4 pi ideal vector cross r cap by r square. If you expand this, you will get ideal sin theta by r square. Suppose if you write here as r vector, here you have to put r cube so that r and r cancels, denominator will become r square. We have two applications in Biot-Savart law. Infinitely long straight conductor. Magnetic field at a point due to infinitely long straight conductor carrying current. B is equal to mu naught I by 2 pi r, where r is the distance between the center point of the wire and the point where you are considering the magnetic field. Can be D, it can be A, it can be X, anything. Mu naught I by 2 pi r. Circular coil, point along the axis of the circular coil carrying current. Point along the axis of a circular coil carrying current. There, B is equal to mu naught I by 2A. General formula, B is equal to mu naught I A square by 2 into A square plus X square whole power 3 by 2. This is a circular coil. Here you want have the point P. Radius is A, the distance is X. At this point P, this is the magnetic field. Suppose this point P is taken to be the center, then I can write X is equal to 0. When you say X is equal to 0, mu naught I by 2A. For n turns, B is equal to mu naught Ni by 2. Number of turns. One turn means this is the formula. N turns means mu naught Ni by 2A. This concept only are using in tangent galvanometer. Tangent galvanometer concept. When a magnetic needle is suspended between two crossed magnetic field, then the magnetic field due to the coil, magnetic field due to the earth, this two, d by dh is equal to tan theta. Then the magnetic needle will come to rest in the direction of resultant of both the fields. Resultant of both the fields. B by dh is equal to tan theta. B is equal to dh tan theta. B is circular coil carrying current for n turns. Mu naught Ni by 2A is equal to dh tan theta. In practicals, we are calculating dh. So dh is equal to mu naught Ni by 2A tan theta. I by tan theta only practically we are calculating. Mu naught n by 2A is a constant. Mu naught is 4 pi into 10 power minus 7. N is the number of turns and A is the radius of the coil. then BH is equal to mu naught Ni by 2a tan theta. For different values of current, what is theta we are calculating. Okay. Motion of a charged particle in a magnetic field. Motion of a charged particle in uniform magnetic field. When a charged particle enters a magnetic field, it follows a circular path. Work done is 0, so it moves in a circular path. So, F centripetal force is equal to F magnetic field force we are equating. Centripetal force is mv square by r. Magnetic field force is bqv sin theta. Maximum value means sin 90, so it will become 1. So 1v get cancels. V by r is equal to bq by r. So the ratio V by R is constant. In this case, the ratio V by R is constant. This principle only we are using in cyclotron. Cyclotron is a particle accelerator. Cyclotron is a particle accelerator. Proton, neutron, alpha particle, this and all, when it comes out of the source, it is not initiating nuclear reaction. To initiate a nuclear reaction, we need extraordinary high velocity. That extraordinary high velocity is provided by particle accelerators. One accelerator we saw in chapter 1, electrostatics, Van de Graaff generator. This is another accelerator. This is given in this chapter because it follows magnetic effects of current principle. The same concept here, V by R is equal to BQ by M. You know very well, omega is equal to V by R. V is equal to R omega. Relation connecting what? Linear velocity and angular velocity. So I can write 2 pi by T is equal to V by R. That is BQ by M. T is equal to 2 pi M by BQ. Time period of revolution by the charged particle when it is moving in the D's of a cyclotron. You know the theory, formula alone we are writing. Frequency F is equal to 1 by T. That is BQ by 2 pi M. Kinetic energy I want to calculate. You can. Kinetic energy EK is equal to half mv square. Half mv into v. You see here, mv is bqr. mv is bqr. mv is bqr into mv square. So what we are doing here means put whole square here, then divided by m. So that you will get m square, v square by m, 1m get cancelled. So bqr by m, the whole square. mv is nothing but bqr. So we can write 1 by 2m b square q square r square is kinetic energy of the charged particle moving in the D's of a cyclotron. Okay, fine. Next, force experienced by the current carrying conductor in a magnetic field. When you talk about force experienced by a current carrying conductor in magnetic field, you should know what is the force experienced by a single charge. That is called magnetic Lorentz force. Magnetic Lorentz force FL. BQB sin theta. Q into B cross B. Single charge. I want to calculate the force experienced by the entire charges, that is electrons moving in a conductor. That case F is equal to BIL sin theta. BIL sin theta. Magnetic induction, current, length of the conductor, angle between the magnetic field and the current carrying element. BIL sin theta. Maximum value means BIL. Suppose you have two conductors, force between them I1, I2 separated by a distance A. What is the force between these two conductors? Means mu naught I1, I2 by 2 pi A into L. Force per unit length I need, sir. Put this L here. Force per unit length is equal to mu naught I1, I2 by 2 pi A. Using this derivation only, we are defining the term ampere. I1 1 ampere, I2 1 ampere, A distance between them you call it as 1 meter. Then 4 pi and 10 power minus 7 is substitute. You will get 2 into 10 power minus 7 Newton per meter length. From that only we are defining ampere. Fleming's left hand rule. Forefinger represents direction of magnetic field. Middle finger represents direction of current. Then thumb represents direction of force experienced by the conductor. Okay. Next, torque experienced by a rectangular coil. Torque experienced by a rectangular coil. Whenever a rectangular coil is placed in a magnetic field, four different forces are executing. Two forces equal and opposite cancels. Remaining two forces will try to rotate the body. That rotating force only we call it as torque. Tau is equal to NBIA sin theta. Number of terms N. NBIA sin theta. For a solenoid, magnetic induction at a point due to a solenoid carrying current. B is equal to mu naught Ni, where N is called number of turns per unit length in the conductor. Number of turns per unit length. Ampere circuit law. Closed integral B dot dl is equal to mu naught I naught. Closed integral B dot dl is equal to mu naught I naught. So in this case, when you expand this BDL cos theta dot product, straight conductor you take using Barrett's law. Magnetic field will be in the surrounding. BDL cos theta 0 to 2 pi r, if you integrate that particular equation, you will get the final answer as BDL cos theta. That is Ampere circuit law. Barrett's law, Ampere circuit law we can interpret. Okay, fine. Moving coil galvanometer. In the case of moving coil galvanometer, two couples are acting. One is moment of deflecting couple, MCG, moving coil galvanometer. Moment of deflecting couple, that is another term, torque, is equal to moment of restoring couple, that is K theta. K is called torque constant or torsional constant or coupled per unit twist. Anything you can take. From that you are calculating I is equal to K by NBA into theta. That is I is equal to G theta. Theory of moving coil galvanometer. This is a principle used in determining current sensitivity and voltage sensitivity of a galvanometer. Current sensitivity. Take this equation NBIA is equal to K theta. Theta by I we call it as current sensitivity. Theta by I. So I can write NBA by K. Voltage sensitivity. Voltage means theta by V we need. V means we have to calculate current into resistance. G is called galvanometer resistance. I into G. No, sir. I will take RG as the galvanometer resistance. You can very well take. It's only a notation. G we have taken as a resistance here. Is equal to NBA by kg. Conversion of galvanometer to ammeter, galvanometer to voltmeter. Next topic. Conversion of galvanometer to ammeter. Connect a low resistance in parallel with the galvanometer. That galvanometer and low resistance together we call it as an ammeter. Connect high resistance in series with the galvanometer. That combination we call it as voltmeter. Galvanometer with low resistance in parallel. That only we call it as shunt resistance. Shunt resistance means connecting a low resistance in parallel. So Ig into G is equal to Is into S. Voltage across the galvanometer, across the shunt. Parallel connection, potential difference is same. So I can write Ig into G is equal to Is into S. Rearrange, S is equal to, because the total current here is divided Ig plus Is. Ig by I minus Ig into G. Ig by I minus Ig into G. Suppose you are using galvanometer with a high resistance in series, current passing through. You take it as Ig or you take it as I, both are same. In series, current is constant. In parallel, potential difference is constant. So, Ig into G by Ohm's law, V is equal to IR. But here it is G alone means you can write Ig into G, but two resistors. So, we have to add R plus G. R plus G is equal to V by Ig. R is equal to V by Ig minus G. So, for converting galvanometer to ammeter, you connect a low resistance in parallel. For converting galvanometer to voltmeter, you connect high resistance in series. Okay. So these are the formulae for magnetic effects of current chapter. Based on what we have studied, we will go for some problems. One by one, we will see.